Numerical analysis of single pile in soft clay. Abstract: this paper aims at analyzing the load deformation characteristics of a single pile of varying length, 5, 10, 15 m, and varying diameter, 0.4, 0.5, 0.6, 0.8, 1 m, in cohesive soil with varying cohesive values, 10, 20, 30, 40 kn/m superscript 2, using PLAXIS 3D software. The results of the analysis has been compared based on the safe bearing capacity of the pile under different conditions. A 3D numerical model was developed to simulate the single pile in clay soil. Variation in safe bearing capacity of pile with cohesion for piles of different diameter and different length were studied. The extensive parametric study concluded that there is a linear variation between SBC and diameter of pile, SBC, and cohesion of clay soil, and SBC and length of pile. Keyword: single pile, safe bearing capacity, cohesion, PLAXIS 3D. Introduction. Piles are deep foundation used when shallow foundations do not satisfy the settlement and bearing capacity criteria. Piles are classified based on the material of the pile, the displacement properties, and the nature of load support. The pile load displacement characteristics of single pile are affected by pile properties, soil properties, installation methods, and loading conditions. Pile foundations transfer the superstructure loads to deeper part of the soil strata. Based on the nature of load support, end bearing and friction pile, the piles transfer loads either to an end-bearing stratum or via the skin friction developed along the shaft of the pile. In soft soil, the pile makes use of the strength of the soil by skin resistance along the shaft of the pile. Here the load transfer of piles is the sum of the toe resistance and skin resistance in soft soils. 1. Methods adopted to find the bearing capacity of piles are static formula, dynamic formula, and field load tests. The static formula method relates soil shear strength to the skin friction along the pile shaft and to end bearing below the pile point. Both the skin friction and the end bearing resistance are used to calculate the bearing capacity of piles of any dimension in cohesive and cohesion-less soils too. Many studies have been performed to determine the behavior of axially loaded pile in cohesive soils. In this study, a comparison of the safe bearing capacity of single pile of different length and diameter are tested in cohesion soil of different cohesion values. 2. Model validation. A validation of soil model. The Algae bridge pile load test is an axially loaded validation case, which is widely used by researchers for validating new soil models. The Algae bridge pile load test was carried out near Frankfurt. During the test, load cells were installed at the foot of the pile to measure the loads that are carried directly by the pile base. The test results and other parameters are presented by Engine ETAL13. The Algae bridge pile load test considers an axially loaded pile with a diameter of 1.3 m and a length of 9.5 m. The groundwater table is approximately 3.5 m below the ground surface. The pile was modeled in the Moore-Coulomb soil model using PLAXIS 3D software. Embedded pile was used to model the pile. Point load was assigned to the pile top and the soil was meshed. Medium mesh was used for meshing. Figures 1 and 2 SHOWS the modeling of soil and pile using PLAXIS 3D. The pile was modeled in the Moore-Coulomb soil model using PLAXIS 3D software. Embedded pile was used to model the pile. Point load was assigned to the pile top and the soil was meshed. Medium mesh was used for meshing. Figure 3 compares the experimental load displacement behavior of piles with that obtained using PLAXIS 3D software. From Fig 3, it may be noted that, except at the initial linear elastic stage, the experimental and theoretical load displacement behavior of pile are comparable. Hence, the modeling of soil and pile using PLAXIS 3D has been validated and the same approach can be followed for further study. 3. Parametric study safe bearing capacity of pile. The load deformation analysis on a single pile of varying length, 5, 10, 15 m, and varying diameter, 0.4, 0.5, 0.6, 0.8, 1 m, in cohesive soil with varying cohesive values, 10, 20, 30, 40 kn/m superscript 2, using PLAXIS 3D software was studied. The results of the analysis has been compared based on the safe bearing capacity of the pile under different conditions. A 3D numerical model was developed to simulate the single pile in clay soil. As the first step of the modeling process, the geometry of the single pile and the soil block were defined. The soil volume was modeled as a 10-noded tetrahedral element and has a depth twice the length of the pile in more column soil model. The soft clay was modeled in the undrained condition. The piles are modeled as embedded beam element with special interface element. The pile-soil interaction for an embedded pile involves a skin resistance and a tip resistance. The input parameters that are required for modeling the soil are modulus of elasticity, Poisson's ratio, angle of friction, dilatancy angle, and unit weight of soil 4. The modulus of elasticity of cohesive soil has been determined as per the following relation 5. With respect to the pile, the parameters like modulus of elasticity, Poisson's ratio, skin friction per unit length and end resistance are required for the analysis. The skin friction per unit length and end resistance of pile were determined as per the guidelines specified in BIS for the calculation of pile capacity in cohesive soil 6, and accordingly, following equations were used. The load capacity of pile for a specified displacement is higher for soil with higher value of cohesion. Similarly, as the diameter of pile is more, the load capacity of pile for a specified displacement is higher. These behaviors are expected, as the end bearing capacity as well as frictional resistance of pile shaft are proportional to the diameter of pile and the cohesion. Similar behavior has been observed for piles of different length. 4. Safe bearing capacity of pile. The safe bearing capacity, SBC, of piles could be determined from the load displacement graphs of piles and as per the guidelines specified in BIS 7. According to this code of practice, the safe vertical load on single pile for initial test shall be least of the following. A. 4 piles up to and including 600 mm diameter. I. 2/3 of final load at which the total displacement attains a value of 12 mm. 2. 50% of the final load at which the total displacement equal to 10% of the pile diameter in case of uniform diameter piles. B. 4 piles of diameter more than 600 mm. I. 2/3 of final load at which the total displacement attains a value of 18 mm. 2. 50% of the final load at which the total displacement equal to 10% of the pile diameter in case of uniform diameter piles. Figure 5 explains the method of determining the safe bearing capacity of 10 m long, 0.50 m diameter pile in soil having different cohesion from the load displacement curve, as a typical example, and is self-explanatory. Out of the two values, the least one is taken as the SBC. In a similar way, the SBC of all other piles were determined, and the details are presented in tables 4, 5 and 6 for piles of length 5 m, 10 m, and 15 m respectively. It may be observed from tables 4.2 to 4.4 that, in all the cases considered, the criteria of 2/3 times load corresponding to 12 mm is critical when compared with the criteria of 50% of load corresponding to deformation equivalent to 10% of pile diameter. 6. Conclusions. Based on present study, the following conclusions could be made. 1. There is a linear variation between SBC and diameter of pile, SBC and cohesion of clay soil, and SBC and length of pile. 2. For low value of cohesion, 10 kN/m2, difference in the SBC of pile with different length and diameter is not significant. However, as the value of cohesion increases, up to 40 kN/m2, the difference in the SBC of pile with different length and diameter becomes significant. 7. Acknowledgement. I would like to express my sincere gratitude to my guide Professor Berlin Sabu for her valuable guidance, care, and timely support throughout the thesis work. I am extremely grateful to the Principal Professor Matthew K. Mar Athanasius College of Engineering, for providing me with best facilities and atmosphere. I take this opportunity to thank Professor Lenny Stephen, Head of the Department, Department of Civil Engineering. Above all, I owe my gratitude to the Almighty for showering abundant blessings upon me. Acknowledgement would not be complete without acknowledging my gratitude to my beloved parents who have been pillars of support and constant encouragement throughout the course of my thesis work.